Okay, great. My name is Carmen Frantel. I'm a staff consultant with Copeland Building and Blow Consulting, and today I'm going to be presenting on the 4 barriers in a contemporary context, and then I'm going to mix in a little bit of our Wild West presentation, which is case studies on some of the building and blow failures that we've seen in the field. So just as a high-level overview, the bulk of this presentation is really going to explore how we manage moisture and apply that to design considerations and quality assurance, quality control, or QA/QC measures across all 4 barriers in exterior wall assemblies. And when I say moisture management, we're really looking at 3 types. So we've put them on a podium here. And to be clear, this is not the podium where we're going for gold. We've ranked this based on speed and severity with which we see issues in the building envelope. So at the very top, we've got water leakage. In second place, we have condensation, and with the bronze medal, but still not insignificant, we have vapor diffusion. So what are the 4 barriers? Is the water barrier, the vapor barrier, the air barrier, and the thermal barrier. And even though I'm listing that there are 4 different barriers, what's important to note is that it doesn't necessarily have to be 4 unique materials. So some can be dual purpose or dual plus purpose. So for instance, you might have something like a product in your wall assembly that is acting as the air barrier. You could very well also have a product that acts as an air and vapor barrier. Or there are some products, which I'll go into in a little bit, which act as an air and thermal and vapor barrier. And each one of these 4 barriers is related to moisture movement. So failure in any single one of them, or a product that's acting as multiple, can compromise the entire assembly. So let's take a closer look at the function that each of these barriers serve. So we'll start with the water control layer. So this is essentially going to be your first line of defense. It's going to be what prevents rain and bulk water entry from getting into your building. So products, examples of this include water-resistant barriers. So you may see products like Blueskin, Tyvek, the green of Zip Sheathing. It also includes things like draining provisions, so a drainage cavity or a drainage plane, and flashing. Next, we have vapor control. So this is going to manage vapor diffusion, and vapor diffusion at a very high level is essentially moisture molecules that are able to pass through a material themselves. So we like to think of it as kind of like the ghost of moisture movement. And a vapor barrier is essentially a material that is going to slow or prevent that vapor from diffusing through that material. It's going to block the ghost from going through the wall. So examples of this would be sheet products. You can have some elastomeric coatings, depending on their permeability, act as a vapor barrier. You can also have spray foam or foil-faced insulation, specifically the foil facing of it. Then we have air control. So the air barrier prevents air leakage, and the reason that we care about this, and what I'll get into a little bit later, is that air carries water. So examples of this, again, can include sheet products, it can include fluid applied products, spray foam insulation, or rigid insulation, specifically when it's taped and sealed at the seams because you want continuity. And finally, we get to our last barrier. That's going to be the thermal control. So those who have lived or worked in cold climates, like myself, love this one because it keeps us warm. But from a moisture perspective, it's also really important because it can contribute to your condensation risk. So the thermal barrier is going to include things like your insulations. So this will be batt insulation, spray foam insulation, rigid insulation, any of that. And again, like I said, just because there are 4 barriers does not necessarily mean that there are going to be 4 distinct products. So as you saw here in thermal and back in air and then also in vapor, something like spray foam could act as multiple barriers in your wall assembly. All right, before we dive in, I'm going to take a step back and look at some basic terminology. If you already know these terms, bear with me, but it's good to have a refresher. So first we have relative humidity. So this is going to be the measure of the air's moisture content at a specific temperature. And this is important because warm air can actually hold more moisture than cold air. So for instance, let's say 40 degrees can hold 6 raindrops of water, and let's say 90 degrees can hold, what did I put on there, 24 raindrops of water. So if somebody tells me oh, there's 50% relative humidity, I have no idea how much moisture you're talking about because you haven't given me the context of the temperature. So 50% relative humidity at that 40 degrees, you would be talking about 3 raindrops of water. 50% relative humidity at 90 degrees, you'd be talking about 12 raindrops of water. So again, this is really just showing that relative humidity has no meaning while isolated. So to understand how much moisture we're talking about, we have to place relative humidity in the context of temperature. So we can then apply this to vapor drive. So vapor moves from higher concentrations or higher pressures to lower concentrations or lower pressures. And in buildings, this typically means from warm to cold, because as we just talked about, the warmer air can hold more moisture, usually has more moisture than the cooler air. And so this is kind of the world's way of trying to get back to equilibrium. It's going to take the really high concentration, the warm, the wet, and it's going to try and balance it out with the cooler and the drier so that it's balanced on both sides. And the reason that we care about this vapor drive and the vapor drive direction really boils down to climate. So in a cold climate, the vapor drive is typically going to be from the interior to the exterior, and that's because in cold climates, it's snowing outside, we're going to be heating, warming our interior, humidifying our interior. If you then hop on a plane and you travel to a hot, humid climate, the vapor drive is going to flip. So it's going to be from the exterior to the interior, and that's because they're typically cooling the interiors. They're putting AC in, they're dehumidifying. And with this, we also have to consider season. So we have to think about climate first, but then we also have to think about season. That's because in some climates, the vapor drive can actually flip depending on the season. So again, depending on if you're heating or cooling the interior, what their interior conditions are relative to the exterior. All right, so let's talk dew point. For those from the East Coast, this is a favorite slide because of the picture on it. But dew point is essentially the temperature at which condensation forms. So if any surface falls below this temperature, you're going to see condensation or water droplets on that substrate. So you could see this on things like ice beverage containers in warmer weather, because again, that ice that's cooling the drink or the cold drink itself is making the surface of that plastic cup cold. And then you go out into a warm environment where, like I said, because warm air holds more moisture, you've got more moisture just in the air. And that moisture is going to be coming in contact with this cool surface, the plastic cup, which is below the dew point. And it's going to take the moisture from the air, condense on that cold surface, and the water droplets are going to form. And similar to ambient temperature, which is like the temperature that we feel on our skin every single day, the dew point is going to depend on the season and the day. This really brings us to the core of this presentation, which is that despite there being advances in technology, contemporary buildings are increasingly vulnerable to moisture damage. And the underlying question is, why is that? Well, to start, buildings today, we are building more airtight and more insulated. So contemporary air barriers and sealing techniques have dramatically reduced the natural air leakage that we have. In part, we are being guided this way by the current energy code with the newest additions requirements. On top of that, we are adding more insulation to assembly, again, in aggressive energy efficiency efforts. So together, this building more airtight and building more insulated are contributing to reduced drought potential. And that just means that when moisture gets into the wall assembly, it takes longer for it to give out. So the bottom line there is that our wall assemblies are going to be less forgiving. On top of this, we have more complex designs. So you take the fundamental principles of what I'm talking about here and you apply it to a rectangle box, and it might be pretty straightforward. I actually probably wouldn't give this presentation as often as I do if that's what we built, but it's not. I do have a pitch for the stone shoebox if anybody wants to stick around after the presentation and hear me out on it. But for the people in this room, for architects in general, there's some wild creativity. And so we're not building rectangle buildings. We realistically see designs that have geometries like the Weizmann Art Museum here, which is located in Minneapolis, or maybe less drastically, we're seeing a lot of buildings with multiple cladding materials. And then once it looks less soul crushing, you stick a ton of holes in it for natural light and maybe some mechanical ventilation to help with the whole more airtight and more insulated, less drying potential trend that I've just discussed. And then finally, we have to consider environmental factors. So we have higher interior humidity levels. What you're seeing here in this picture is actually the interior humidity level at a kind of unique space. So that was at a natatorium, an indoor pool. But Modern Comfort is typically operating around 35 to 45% relative humidity. And then we also have to factor in the changing climate patterns. So every single year, every single summer since the year 1980, with the exception of 2, has either been warmer, wetter, or both. So ultimately, when we look at all of these things across the board, we have factors and challenges that we're not really getting away from. Because of energy efficiency portions of the code that are guiding us to build more airtight, we aren't really changing our trajectory there. And quite frankly, we shouldn't want to. The power of an architect's creativity isn't going anywhere. While I would love for my stone shoebox idea to take off, I don't anticipate it being the 2026 architectural trend. And then the climate and the comfort trends historically haven't changed. We don't see them changing going forward either. So knowing this, what we're asking is, if we can't go back, how do we face the challenges that contemporary buildings are posing today? Well, we can show you what didn't work. We'll start with the Marina Apartment. These are luxury apartments that are located in Quincy, Mass, and were constructed in 2017. So this is less than a decade old. And the first problem that the client came to us with is that there were indoor air quality issues, specifically that tenants were getting sick and moving out. And the management wanted to investigate this further because, number one, again, their tenants were getting sick, but also several of their units were unoccupiable, and so they couldn't be making rent on those units. It was just essentially sitting vacant. So this building had flat panel fiber cement siding, or fiber cement cladding pieces, and that cladding was important because it had no water shedding mechanism built into it the way that, say, the clapboard cladding might. So a fair amount of water gets behind these panels, even if they're installed 100% perfectly. And what this is really telling us is it makes the backup control layers, or those 4 barriers, all the more important in actually managing that water and the moisture. So we began to open up the exterior wall assembly, and this is what we were seeing. Apologies if anybody is eating while watching me present this today. It's not exactly the most appetizing to see on your screen. So essentially what we found here was, number one, they had poly installed at the interior. So this is going to act as an interior vapor barrier, and again, it's going to reduce the drying potential. It also is going to delay the signs that they saw in the interior. So again, they weren't seeing things on the inside like warped floorboards. They weren't seeing things like bubbling paint, peeling interior finishes. They were just getting sick. So what we also saw on the exterior when we opened it up is that they had applied a fluid applied membrane directly on top of OSB. So OSB was their sheathing material in the exterior wall assembly. And then they also did not have a dedicated drainage plane. The fluid applied membrane that was installed onto that OSB also was semi-permeable. So the expectation of this product was that it was not intended to perform under continuous hydrostatic pressure. It wasn't a waterproofing membrane. It wasn't expected to have that kind of capability. So if you want to point the finger and blame, the fluid applied in and of itself was not necessarily bad. The OSB in and of itself, while it's not something that I would have recommended for the sheathing, it's not necessarily bad. The drainage plane, not having one, again, in and of itself, not necessarily bad. You can design correctly with that. But when you combine all of these, and then on top of it, you pile on that the cladding, as we mentioned before, is a flat panel, so it doesn't have that inherent shedding capability. You just have a much more elevated risk of issues. So fluid applied, OSB, no drainage plane, flat cladding. Those 4 together, each incrementally, are increasing your risk. We continued to open it up. We also found deteriorated insulation within the deteriorated wood framing and crumbling sheathing. We call this oatmeal OSB. And unfortunately, these issues were really widespread. It was building wide. There were, like we mentioned before, significant health and safety risks, and it all came with a very high repair cost. So we had widespread replacement of the enclosure components, including the wood framing. We also had several rounds of costly investigation just to pinpoint these issues. And during all of this time, the occupants were reporting health concerns and moving out. And so that rent on those units was not collectible because they were vacant. So if we think about which barrier really contributed primarily to these issues, it's going to be the water control layer, or the water barrier. Control layer and barrier in the purpose of this presentation are really interchangeable. So again, the semi-permeable fluid applied membrane plus the OSB plus the flat cladding plus the no drainage plane all combined are going to give you the elevated risk that tipped this building over the edge of proper bulk water management. So if they had had something like a drainage plane, they might have been okay. The fluid applied in this case, it's semi-permeable, but the fluid applied wouldn't have been under as much hydrostatic pressure for as prolonged of a time because, again, that moisture, that bulk water would have been running down drainage plane. There would have been airspace with some ventilation in there for it to dry out. If they had used something like a more robust impermeable sheet product, I'm talking about something like a permabarrier. Now, when you install something like that, you also have to consider condensation risk and exterior insulation and all of that. But if we took condensation off the table and we were just talking about it from a bulk water management perspective, if they had used an impermeable, more robust sheet product, it likely would have been okay. If they had not had an interior vapor barrier, it might not have been as bad, and they probably would have seen symptoms sooner, or they might have just had a longer runway before these issues started to develop. But that wasn't the leading cause. If they had used plywood instead of OSB, again, it might not have been as bad because, again, OSB has a higher moisture sensitivity. So plywood perhaps would have performed a little bit better in this situation, but again, that's not the driving cause here with this building envelope failure. We'll go into our next case study, which is going to be these luxury condos in Cambridge, Massachusetts. We joke all the time at our office that a lot of our projects that are the worst happen to have the word luxury either in the title of the building or the real estate listing for it. So this one was a luxury condo, $1.4 to $1.65 million sales price for the units, 15 to 20 units in the building, and it was built around 2015. So again, about a decade old at this point. This is a past project of ours, so we were investigating this when it was less than a decade old. This project has zip sheathing with fiber cement siding and then spray foam insulation on the interior. So, and the exterior wall assembly does not, again, have an intentional drainage plane, or at least not that we uncovered in our investigation. So the client in this case called us because they were starting to notice interior damage, so floor staining, peeling paint in the units, things like that. And unfortunately, the evidence they were seeing on the interior of water damage came pretty late in the game because the spray foam insulation was actually masking the water issues occurring in the assembly for a pretty long period of time. So again, they were starting to see things at the interior, so we can see that here with the deteriorated flooring. But when we went and opened it up to the exterior, it was much worse on the exterior. So the exterior components were completely deteriorated. We get a lot of questions when people see photos like this of, is zip sheathing bad? And we like to call zip sheathing the building envelope version of 2-in-1 shampoo. So it's not necessarily that the product is bad, but it does require careful detailing, installation, and understanding of the environment in which you're placing it and the limitations of the product. So On top of, when we opened it up, we saw the crumbling zip. We also saw that the base window transitions had discontinuous flashing and blocked drainage paths, so blocked weeps and locations where water was intended to be running out of the assembly, but was covered or, for one reason or another, not able to get out. So we looked at about half of the building overall. There's nothing to say that the second half would not have looked exactly like the first half that we look at, although we were asked to stop looking. I think there just got to be a point where it was too much of a dumpster fire. And what we did find on the first half of the building that we uncovered was evidence to support a need for significant envelope restoration. That was removal and replacement of a significant portion of the exterior wall assembly. So that was the insulation, the sheathing, the cladding, removal, reslip, and replacement of about 5 to 10% of the roof area. And then also complete removal and reinstallation of all of the windows in the condos in order to flush them properly. So if we think about the barrier that was the primary contributor to the issues experienced here, once again, it was going to be the water control layer or the water barrier. So this project couldn't handle the bulk water adequately, similar to the last project. Could we have used a full shampoo and conditioner set instead of a 2-in-1? Sure, that may have done a little bit better. Again, it would have just extended the runway, perhaps, of the issues that we were seeing. The fundamental underlying issue was really related to the design. So the design, number one, it didn't specify that drainage plane, which we like to see for drying potential, and bulk water management. And then number two, it wasn't well enough documented in the construction documents put together by this architect, what to do at transitions. So when I say transitions, like one coming to mind is this one right here. So the base of the window to the exterior wall. The ambiguity in the drawings essentially meant that the contractor didn't explicitly know where drainage was needed. The finger can also kind of be pointed at the contractor and saying that they also made poor choices in not asking clarifying questions about it. But the design intent, again, ambiguous, and there was kind of this gray area between design team and execution team. And the ball was really dropped. And then the last case study that we'll look at is an Ivy League natatorium. So this is an indoor pool facility with a 750,000 gallon collegiate swimming pool. The exterior wall assembly here is an insulated CMU with brick veneer. Again, because it's an indoor swimming pool, we have a very unique high humidity environment. And the client called us up and said that they were having issues in closet spaces and locker room changing areas with condensation, but really in the winter months, ice forming on the interior surface of the exterior wall. So in the locker room changing room, they were having ice on those walls. And something to note here is that of the projects where we have interior condensation issues reported, it's almost always occurring in a space with an abnormally high relative humidity level for one reason or another. So for example, something like a pool environment, it might also be, a specific unit in a condo building is having a lot of issues. We walk in and we see like 4 different humidifiers running and we think, okay, yeah, this makes sense. So elevated moisture already is going to be contributing to this. This project actually had a lot of issues with thermal bridging at the base of wall condition and not having enough insulation. So the interior surfaces were cold in the winter, again, below that dew point that I talked about before when we saw the Dunkin' Donuts coffee, and moisture from the high relative humidity environment and warm environment, because again, it's a natatorium, it's an indoor pool. That high humidity and high temperature, which holds a lot of moisture, that moisture was accumulating on those cold surfaces, which were below the dew point, and then ultimately freezing in the winter. So here we can see 75% relative humidity, 80 degrees. So that's a lot of water. And then here we're seeing a third model with the temperature gradients kind of through it, and we can see that the interior surface is quite cold. So what to do about it? Well, option one was to look at reducing the amount of moisture in general, so bringing down the relative humidity inside. But this is pretty much a non-starter for an indoor pool. You've got 750,000 gallons of water sitting in a space. You're not going to bring down the relative humidity. Option 2 was to do a complete reclad of the building to add exterior insulation. The client wasn't really having any other cladding issues at this time, and the condensation was more than anything to them an annoyance, and so they couldn't really justify the expense or the disruption to the facility with taking on such an extensive project. So we ended up leading to an option 3. We increased ventilation at the condensation planes. So essentially we interrupted the insulating properties of the stagnant air. So in closet spaces and in changing pods of locker rooms, when that door is closed, the air is not really moving. So we essentially increased the ventilation and air movement there, thereby warming the condensing surfaces, so keeping those interior surfaces of the wall above that dew point year round to reduce the condensation potential. So it was a little bit more of a mechanical fix than building envelope fix, again, because the building envelope fix was going to require a significant amount of disruption to their facility. So in terms of the primary contributor, which barrier do we think that this one was? So this one's going to be thermal control. Like I said, we have a significant amount of thermal bridging and not enough insulation at that base of wall condition. And when we see things like these case studies and premature building envelope failures or building envelope failures, honestly, in general, a very popular game for our industry is the blame game. So people will blame execution. So that's going to be poor workmanship, deviations from the plans or specs. I put it perfect on paper, and when the contractor looked at it, he just built it on incorrect product usage, damaged materials, things like that. We'll also point to design. So saying that the construction documents were ambiguous, saying that the design was unsuitable for one reason or another. It didn't meet the location, function, or performance requirements of what it was intended to be. People might say that there wasn't enough consideration to buildability or constructability, which I'll circle back on later in this presentation. People point to maintenance, specifically deferred or improper maintenance, repairs, upgrades, things of that nature. And then finally, people will blame materials, so manufacturer defects, ambiguous installation instructions, or installation instructions that are 600-page long novels that nobody wants to read, buried on, page 414. In our experience of many years of building envelope consulting, the vast majority of issues that we see are really boil down to execution or design failures. Maintenance is a contributing factor, certainly, but it's rarely the leading cause. And materials, quite honestly, are even more rare to be the leading cause. People will say, like, oh, well, the wood framing is rotted. That's failure of the wood. That's true, but the wood framing was probably also kept under conditions that it was not expected to perform properly under. So, for instance, if the wood framing or the wood stud is submerged in water, the wood's not intended to perform well in that kind of environment. So the bottom line in those, again, generally boils down to execution or design. It's also important to note that execution and design typically have an overlap. So architects have a liability, they have a standard of care that they need to meet, but you also have agency to go beyond that. So think about ways to improve your approach to increase your chances of success beyond what's strictly required of you. This kind of helps to cover, like I was mentioning before, this gray area between design and execution. So we like to say, like, what can we do on the design side to make what we hand over to the execution team as idiot-proof as possible? We want it to be easy. We don't want there to be any gray area. So we look at the blame game for the case studies that we just did. For the Marina Apartments, the leading factor for what caused this deterioration is the execution. But there is also kind of supporting factors of design and materials. And when I say materials, I'm not specifically talking about material failure so much as the materials that were chosen. Had other ones been selected, again, maybe it would have extended their runway. So for instance, in the Marina Apartments, them choosing OSB, the OSB in and of itself was not that leading cause, but choosing OSB over something like plywood potentially supported the deterioration rate that we were seeing. For the luxury condos, a very similar situation. So leading deterioration factor was going to be the execution, and then supported by design and materials. And then finally, the Ivy League natatorium, the leading cause there was really, it came down to the design and not having enough insulation. So as we see in these three case studies, design is really a common thread in all of them. Execution is also a key player, and that kind of supports the anecdote that we had before, in that of the many years that we've been doing this, design and execution are the top two leading causes that we've been seeing in particularly bad building envelope failures. So we'll go back and dive a bit deeper into each barrier, and we'll start with the water barrier. So there are two types of exterior walls that you can design. The first is going to be a barrier wall system. So this is going to rely on continuity of watertight materials at the exterior surface of your exterior wall. And this is essentially a single line of defense. So there are no drainage provisions in it. So contemporary examples of this would be something like eaves without drainage, some metal panel wall assemblies. So if you think of something like a warehouse metal panel wall, or like a pole shed, and then precast concrete or block wall with sealant joints and no weeps. And this type of assembly really functions on the principle that the barrier has to maintain 100% integrity, because any breach in this barrier, essentially, that's intending to keep water out, compromises the entire system, right? So water that gets in is not designed to get out. It's basically an all or nothing protection, which comes with a lot of risk. The second type of wall assembly that we can design is called a drained wall assembly, which is going to incorporate a dedicated pathway for water that enters the assembly to exit. So this is going to be most contemporary assemblies that we see today, something like brick veneer, curtain wall with weeps, siding with a drainage plane. So these walls have two lines of defense. The first being the cladding, if I can get my cursor to move correctly, up and down, there we go. The cladding, and then your second line of defense, the kind of suspenders to your belt, if you will be your water resistant barrier back here at the backup wall with your flashing down at the basic wall. So this builds in redundancy, which is preferred, but it still relies on critical features like the continuity of your water resistant barrier at that backup wall, or correct installation of the flashing at the base of wall to collect water and direct it to the exterior. The barrier or the drained wall assembly is only as successful as actually getting the water out. So when we're designing drained wall assemblies, flashing is incredibly important. And the function of flashing is to collect the water that gets into the wall assembly and direct it to the exterior. So there are a few key things to consider on the design side when we're designing flashing. So first and foremost, don't penetrate the horizontal surfaces. Like I said, the primary function is to redirect water out of the assembly. And so essentially water is going to be running down that drainage plane with gravity. It's going to collect on the horizontal, so right here, of a flashing. And if we're penetrating it on that horizontal, we're creating a literal hole where water is precisely designed to collect. So we want to be fastening the flashing to our wall assembly on this vertical leg, not the horizontal surface. Second, the flashing has to slope outward in order to direct water away from the building. So any inward slope, somebody might call it a reverse slope, is going to create a path that guides water back towards the wall assembly. So for instance, as we see in this picture here, we poured some water on this flashing ledge, and it actually all just flowed straight towards the exterior wall assembly. So this had a reverse pitch or reverse slope, which we don't want. So we want to promote water drainage away from the building by sloping it to the exterior. Third, we want to provide end dams. So end dams are the raised edges at the end of flashing that prevent water from flowing sideways off of it. So like I mentioned just previously, water collects on the horizontal surface of the flashing. As it comes down that drainage plane, it's trying to get kicked out. Again, on its way, it's going to pass over that horizontal surface. But it can also move laterally along that flashing. So without proper end dams, water can actually travel laterally and go into the wall assembly at the ends, basically bypassing the drainage system entirely, the flashing piece. So what we want to do is essentially cap it at both ends to make sure that any lateral movement stays on the flashing and is still directed to the exterior, again, assuming that we have that slope to the exterior that we want to be seeing. On the design side, we also want to make sure that the documentation directs the contractor or the execution team to shingle lap materials. So shingle lapping is essentially going to mean that each layer overlaps the one below it, so something like this, so that water, when it's flowing with gravity, flows over the joints, not behind that. So when you have reverse laps, something that looks like this, you can get a material that fish mouths, so it essentially starts, the bottom one starts to peel away a little bit, and looks like a fish's mouth when it's open in terms of the gap that it creates between the materials. And then any water that's running down, again, that drainage plane with gravity could get into, in between those materials, getting to the sheathing or getting into the wall assembly instead of guiding it out and away. So when you have reverse laps, you have to continuously seal or terminate that lap with sealant or with mastic. And these continuous terminations are reliant on the workmanship of the sealant or the mastic installer. So if you have a reverse lap and the sealant is installed in a manner that is not continuous, it can provide a pathway in. Which again, if we're looking to kind of idiot-proof our designs, let's make it easy for ourselves, work with gravity, call out shingle lapping. So from a quality assurance, quality control perspective, we can do water leakage testing and construction administration or construction oversight to verify that the water barrier is continuous. But along with this, on the design side, we want to specify the exact water testing requirements that we want to see in the documentation. So include things like the approved test method. What type of water testing are we doing? We want to see things like the number of tests that we're looking to see, test locations, maybe also when you want to be doing these tests. If you just say flat out, I want water testing done, they could come along and do it at the very end. So when do you want to see this done? Explicitly put that in your documentation. Okay, we'll look now at vapor. So if we think back to the earlier slide on vapor drive and climate, because vapor flows in different directions depending on the climate that you're in or potentially depending on season, you have to be intentional with where you place the vapor barrier in your wall assembly. So the bottom line of this is don't place it on the wrong side of the assembly. So if we have vapor drive from exterior to interior and we put a vapor barrier at the interior, we're putting an impermeable material right where water's going to collect, and it's going to trap moisture in our walls. This can be problematic in any environment if we put it on the wrong side, but particularly less forgiving in hot, humid climates. Again, because that warmer air carries more moisture, can do damage faster. So think about the climate that you're building in. Think about the vapor drive direction. And then place the vapor barrier on the correct side of the wall assembly for that climate and that vapor drive direction. All right, let's chat interior vapor barriers. So this would be materials like poly sheet, vinyl-based wallpapers, oil-based paints, foil facing of interior insulation. So like I mentioned on the last slide, we'll definitely run into problems with this if we're placing it on the wrong side of the assembly. So if we're placing it kind of on the end location of the vapor direction. But even in climates where this theoretically could work with the vapor direction, the vapor barrier is still risky. An interior vapor barrier is still risky because it can block the essential drying path to the interior. So this can, again, reduce drying potential overall, but it can also hinder early warning signs of moisture problems in your wall assemblies. So the interior warning signs you might be looking for, again, is something like peeling paint, interior finishes being damaged, warped floorboards, not necessarily like a leak or bulk water. And things like that are hindered, or I should just say masked and delayed when you have an interior vapor barrier, essentially prohibiting the moisture from getting to the interior and showing those signs. So worse than just putting it on the wrong side of the assembly or putting it on the interior is creating something called the vapor trap. So this is essentially when you're going to have a vapor barrier material on both the interior and the exterior of the assembly, which means that moisture trapped can't dry in either direction. So if there's no chance for the assembly to dry in either direction, then when water gets in, there's absolutely no forgiveness for it to dry out. So that leaves your only option for repair or remediation as cutting open the assembly and replacing what got wet. So we see this all the time with things like single ply roof assemblies, where we put a vapor barrier on the deck and then we have the rest of our assembly, so insulation, coverboard, and then we put a single ply membrane, which is also a vapor barrier. And we know that when a roof assembly gets wet, really our only option is going to be to cut out what got wet and replace the wet insulation or the wet coverboard and then patch it back up. And we want to avoid this kind of situation in our wall. Think about the material specified. This includes collaboration with interior designers and what is the interior finish going to be, and make sure that you're not creating a vapor trap. So how do we do it right? Well, we can look at something that's been working for centuries, and that's called the perfect wall. So many people have probably heard of this. If you haven't, the idea behind it is essentially that you want your cladding on the exterior, then your four barriers. So this is going to be your water, air, vapor, and thermal. Again, maybe not necessarily four unique materials, but four barriers covered. And then you're going to have your structure interior of that. And this works in all climates. So it's going to work in your hot, humid climate. It's going to work in your cold climate. It's going to work in every climate in between. And so for proper vapor control design, start with the perfect wall. And then in cold climates, where insulation is a little more important, or we need some more of it, we will split the insulation. So that means that we're going to have some insulation on the exterior in line with this four barriers outboard of the structure. And then we'll also put some insulation on the interior. So you kind of have a hybrid wall. And you have to be careful when you're splitting insulation because ratio matters, which kind of leads me into some of the QA/QC that we can do for vapor control, which is going to be using softwares like WFI for hydrothermal modeling. So, for example, what is shown here on the screen is a project where the architect came to us during design and said, hey, we designed this wall assembly, we've split the insulation, and we want you to verify that this won't run into vapor drive or condensation moisture issues. So we took their wall section, we simulated it in WFI, and we looked at how heat and moisture transferred across the wall assembly over the course of several years. And what this told us was that the maximum relative humidity of the materials in the assembly was about 70%, which was safe. So 100% relative humidity is where the air is fully saturated. That's when you're going to get the condensing literal droplets of moisture on your material when the air starts to essentially drop water. So this was a quality assurance check that our team could provide in design development to confirm prior to construction that the proposed assembly would not be conducive to moisture issues with vapor drying. All right, 2 down, 2 to go. So we will move on to the air barrier. So as I mentioned previously, the reason that we care about air is because air carries moisture. And in order for air to carry moisture, unlike vapor diffusion, which we call kind of the ghost of moisture movement, air needs some sort of void. So we're talking about a discontinuity in the material that is serving as your air barrier. Compared to vapor diffusion, air actually carries a lot more moisture. So we're talking in the ballpark of like 50 to 100 times more, which we can kind of see in these photos here. So if these pink dots are essentially moisture, as we see here, if we have that void, this hole, the air is going to carry a lot more of that moisture through than the vapor diffusion, which is kind of death by 1,000 cuts, very slow, small increments. Not to say that it can't cause damage, but it's going to do it a lot slower over time than something like an air leak, which can cause damage quite quick. All right, and we'll get into some design considerations for the air barrier. The reason that I actually have water highlighted along with air on this slide, not a slide error, is because the considerations I'm about to talk about can really be applied to both water and air control, or water and air barriers. So keep that in mind as I'm going through. So first, we want to make sure that the air and water barriers are continuous. So the current energy code actually requires air barriers to form a complete uninterrupted envelope around the building's conditioned space. So what this is asking for is air barrier continuity. And compliance can be achieved for the air barrier in two different ways right now. Number one is that we can achieve compliance through whole building air leakage testing, which is done at the end of construction. Or at the end of air barrier installation, I should say. Or number two, we can do on the design side, which is going to be detailing continuity through all of our details. So this is essentially saying that we need to document all transitions and show continuity of the air barrier through callouts and stuff on the CPs. So if we take this design approach, one way that engineers and architects can kind of gut check this in design for making sure that it's continuous is to do something called the pen test. So what you're going to do is you're going to line up all of your details. So we've lined up two here, for instance, and you're going to trace the air barrier material with your, so we've started to trace it here in orange. And if you have to lift your pen at any point, you've identified a discontinuity. And this is particularly important because, like I mentioned before, like the air barrier doesn't have to be one material. The air barrier can be one material that transitions to another, that transitions to another, that transitions to another. That is going to be the case in every single design. So those transitions is where it's particularly vulnerable. And this pen test can be kind of a first pass check at, do I have an issue at a transition point? If we look at this detail that we've shown here, we can see, again, we've traced our air barrier in orange. This detail is this wall right here. They essentially just hadn't installed the cladding when I took this photo, but we returned the air barrier behind the exterior insulation. And this soffit is kind of in this detail just beyond, you see the break line here. So is there any reason why we wouldn't have just wrapped the soffit in an air barrier membrane? The bottom photo here, excuse me, is a little bit of a hint. So the reason we did this, where we returned the air barrier behind this exterior insulation and then tied it into the roof assembly vapor barrier rather than wrapping that soffit, was because the soffit has penetrations for exterior lighting, which would add complexities in terms of air sealing for continuity if we wrapped it around the exterior here. So actually in the architectural detail, the lighting fixtures were not shown. They may not be shown. Certain penetrations of the exterior might not be shown in an architectural drawing. So know that the pen test does have limitations. You do have to think about factors kind of outside of it. Or if we look at this upper photo up here, so this project was an addition to an existing building. We needed to tie into the existing structure. And things like this, where the addition meets the existing building and how the new air barrier is integrated with the existing air barrier for the existing structure, might not be considered or caught in a pen test because a pen test is limited to 2D space. And again, this condition that we're looking at here is really kind of 3D isometric in nature. Again, pen test is a great tool to have, but be mindful of its limitations or the other factors outside of the pen test that you really have to consider on top of it. And for quality assurance, quality control for the air barrier, we really have a toolbox of qualitative and quantitative tests that we can run. So qualitative tests include things like the bubble test, which you can see here in this top photo. So that's going to be where you essentially put like a soapy mixture over a presumed discontinuity or a transition point where maybe a discontinuity is particularly vulnerable. And then you're going to essentially put a salad bowl over it, which you see here. This is all very technical terminology, just in case you want to tell your friends. And that salad bowl is going to have negative pressure applied. So your salad bowl is going to suck on the soapy mixture. And if I see a bubble, what does that mean? So bubble would mean that you have air movement because a bubble needs air to fill and be formed. So that means if you have air movement, you have a discontinuity in your air barrier. So I love bubbles, but bubbles are not what I want to see in the bubble test because we want continuity, we don't want air movement. You can also use things for qualitative tests like an IR camera with pressure. So at night when it's cold, a leak would appear as warm interior conditioned air passing through to the exterior. Or you can do smoke testing with like a smoke pencil and pressurization to visually see air movement as well. And then we also have some quantitative tests that we can do. So this would be things like field testing of a specified product or whole building air leakage testing, which, as I mentioned previously, that's one of the pathways that you can show compliance with the current energy code if we're not going to go that kind of design and showing in every detail the continuity. And similar to what I mentioned in the QA/QC for the water barrier, what we want to do here is explicitly specify the testing requirements in our documentation. So that would, again, be test method, number of tests, location, things like that. And there are resources for finding this information. So you can find recommendations for things like test method or number of tests in manufacturer literature or applicable ASTM standards. So I've conveniently located some of them on this slide for later reference. I believe I'm recording this, so anybody can take a peek back and look at those. So ASTM is a really good resource. Manufacturer literature for specific products that you're installing is also a really good resource. Right, and we've made it to the last barrier, which is thermal. So as it relates to moisture movement, what we are particularly concerned about, or what's particularly important, is thermal bridges. So at a very basic level, a thermal bridge is a portion of a building assembly that heat can escape through because the material is conductive and it cuts through the thermal barrier. So it cuts through the insulation essentially. So good conductors are materials like concrete or metal. So common thermal bridges that we see are steel studs without exterior insulation, right? Because when you install that exterior insulation, all of a sudden your steel stud's not cutting through it. So when we see steel studs without the exterior insulation, that's a thermal bridge. Window frames or edges. So maybe you felt a freezing cold window frame from the inside in the winter before, but like everything else is completely fine, but the window frame is freezing cold. Also balcony projections. Typically these are, concrete slabs that are literally cutting through the building envelope. Okay, so we can take a look at a case study of a recent project that our team did at a local restaurant. So this was a new construction project located in Massachusetts. It was a restaurant above a below-grade garage. We have the unique condition here of conditioned space, the restaurant, the kitchen, all of that, located directly above unconditioned space, which was their parking garage. So we essentially had a thermal bridge at the base of wall condition from conditioned to unconditioned space around the entire perimeter of this restaurant. So our client engaged us super early on in the design process and schematic design here to do thermal bridging analysis with the goal of limiting the thermal bridging in order to pass the Massachusetts Stretch Energy Code, which it needed to meet the requirements of for permitting. And they also wanted to build in enough buffer, again, in this schematic design phase for compliance with the Stretch Energy Code, the Massachusetts Stretch Energy Code, such that later design changes or submittal substitutions or anything like that wouldn't push them over kind of that threshold into non-compliance. So they wanted to build up this buffer really early when they had the opportunity for less design friction. So we used tools like thermal modeling to gauge the thermal bridging impact at several key details early during the design, one of them being this basic wall detail, which you see here. So this first option, we put split insulation in the wall assembly here. So we've got the exterior insulation, the interior, and the studs. We carry that insulation down the exterior of that below-grade concrete wall. We also put rigid insulation on the interior, all the way down to the footing. And then we put K13 under the slab between the conditioned and unconditioned state. And when we model it, we can see a significant amount of red, of orange, of yellow. So again, that's going to be thermal bridging, heat escaping through that condition and detail. So we ran a second model, a different design. So essentially what we did here was we did a split slab. Oh, if I can find my cursor, we did a split slab here. So what that's going to do is it's going to create a thermally isolated upper portion of concrete separated from the unconditioned space below by that insulation in the middle of the slab. And when we modeled this detail in therm, we got significantly less thermal bridging, right? So we see a lot more blue, a lot more purple. That's what we want to see. And so this project moved forward with this. That's not to say that option one, if we go back here, would not have met the Massachusetts Stretch Energy Code, but with the client-specific goal in mind of creating that large buffer at a point in the design when there was still a lot of pivot room and less design friction, this was what we decided to move forward with collectively as a team. Critical to this project's success really was the point at which we were engaged. So bringing us in early, doing this schematic design at the details where it had large impact. This basic wall detail existed at the entire perimeter of the project. So they knew that whatever design decision they made there is going to have a large impact overall. So this really tells us that we can use tools like this in early design and schematic design to inform good design decisions before we're locked into certain assemblies. So we can catch concerning conditions, again, when there's still a lot of pivot room. Okay, and then I just want to wrap up by stepping back and looking holistically at all four barriers and some design considerations that we should consider kind of across the board as well. So number one, constructability. There are days when I show up on site and I want to get this like tattooed on me. You can tell me later if that's a bad idea. But what I mean by constructability really starts with design coordination. So projects have architects, they have building envelope consultants, they have structural engineers, they have MEP engineers. There's a whole slew of people that kind of cohesively make up this design team. But when each trade is tunnel visioned in their own design, we can end up with things like this photo. Don't end up with things like this photo, right? So we had a structural engineer installing a support column. It wound up being about 4 inches from this building corner, which needed through wall flashing. Somebody also picked the really lucky short straw of getting to roof in this little nook and cranny that was then created between and that back corner, which also needed roofing. So talk it out, catch it in design, we're all friends. Number 2, draft to scale. So this is particularly important when we're working with existing buildings. So you should always field verify the space constraints that are present and depict it accurately in your details. And related to both design coordination and drafting to scale is considering spatial constraints. So that's number 3. So I'm going to go back to this photo that gives me nightmares. So did we consider that if the space was accessible for the required installation method? Likely not, because again, somebody pulled that short straw of getting to roof in that nook and cranny. A similar common example, let's say the structural engineer is installing dunnage to go on the roof, coordinate this with the architect or the designer of record for the roof assembly to know what the height is. So that dunnage is going to be installed first, and you've got to be able to fit a person under to install the roof assembly. So how small do you think your roofer is? Think about space. And then finally, for trade coordination, so this is going to be similar to design coordination, but on the construction side. So identify which specific trades are responsible for each component in terms of installation, and then minimize handoffs between trades where possible. So don't make the sequencing such that it has to go back and forth. This is particularly true at transitions. So something like a parapet where you're going from the roof to the wall assembly, you likely have different trades on it. You don't want it to go from the roofer to the waterproofer to the roofer to the waterproofer to the roofer, because these handoffs are prime time for mistakes or miscommunication to occur, which can lead to discontinuities, again, in those 4 barriers. When it comes to specifying materials, we also want to consider material compatibility. So incompatibility may be materials that are chemically incompatible. That's typically what's thought of first, but it can also be materials used in instances where they're installed improperly. So that can be, for example, like using a membrane under a metal parapet cap that isn't high heat. So when the sun is beating down on it, the membrane essentially melts out from under it. It could also be like our previous example with the Marina apartments, where we had fluid applied installed onto OSB. Again, not the best substrate for continuity, which is required for that product, the fluid applied product, to perform the way it's intended. So using incompatible materials, whether chemically incompatible or in instances where they're not intended to perform correctly, can lead to things like loss of adhesion, brittle material, galvanic corrosion, chemical breakdown, discontinuity, but a big red flag for owners, and what you certainly want to steer clear of on the design side, is that it can void your warranty. So that was a lot of talking, but I want to end with this, which is really 3 key takeaways from the presentation. So if you remember one slide, take this one, or if you're watching the recording and you only have 5 minutes, just watch these 5 minutes. So the 3 key takeaways are, number 1, maintain continuity of the 4 barriers. So think about this in design, verify it in quality assurance, quality control, QA/QC. Number 2, explicitly specify your testing requirements. So again, there are resources like manufacturer literature or ASTM standards that can help with this. And then finally, consider the constructability. The success of a building doesn't live on paper, so make sure it can translate into the real world. Think about the size of your roofer. That's all I have. If anybody has any questions, feel free to reach out to us via email. You can also leave your messages in the chat, and we will be happy to get back to you. Thanks.